Hello class 12. So the topic of the day today is electromagnetic induction. Now this is a topic you already are familiar with because you've done this in class 10 also. So let us kind of review this particular topic again. Now in 1830s, Michael Faraday, he found out that whenever the magnetic flux linked with a coil changes, what happens is there is an induced current or induced EMF in the circuit. And so what he did is, here is a coil and this coil is connected to a galvanometer. A magnet is taken and this magnet is brought with a certain velocity towards the coil, in this case such that the north pole of the magnet is closer to the coil. So initially, say for example, this magnet is not here. So what is the magnetic flux linked with the coil? The magnetic flux linked with the coil is zero or nothing. Now what you're doing is you're bringing this magnet closer to the coil. So what is happening when this magnet comes closer to the coil? The magnetic flux linked with the coil obviously is changing from nothing initially to something when the magnet comes closer. So since there is a change in the magnetic flux, what happens is an induced current is generated. An induced current is generated. Which, how do we know that an induced current is generated? Because this galvanometer shows a deflection in a certain direction. Now, the direction of the current is such that it wants to oppose the cause producing it. So to say, what is the cause producing an induced current in this circuit, in this coil? The cause that is producing the induced current is the north pole of this magnet coming closer to this coil. So the effect, which is the current getting induced, is such that it wants to oppose the north pole, so to say, coming closer to the coil. And how is it done? The opposition is done by, in such a way that a north pole is generated on this side and a south pole is generated in this side, such that this north pole is saying to this north pole of the magnet, please don't come close to me, because it wants to oppose the cross producing it. Alright, so the current is induced in such a way that you have a north pole over here and you have a south pole over here. Now the next instant what you want to do is the same magnet. Now this is closer to the coil. This is closer to the coil, so there is some magnetic flux linked with this coil. Now you take this magnet away from the coil. So what are you doing? You are changing the magnetic flux linked with the coil from some value at this point to nothing when this magnet is taken away. So there is a change in magnetic flux. So since there is a change in magnetic flux, current obviously is induced according to Faraday's laws. That is what Faraday found. And that induced current is induced here. How do we know again? Because the galvanometer shows deflection in the opposite direction now. It's the same coil, same magnet. Now, the current is induced again in such a way that it wants to oppose the cause producing it. So, therefore, the current is induced in such a way that a south pole is generated here and a north pole at the other end. So, what's the south pole trying to say? The south pole is trying to say to this north pole, of course, please don't go away from me, because the cause producing this induced current is the going away of this north pole, and the direction of the induced current, that is the effect, has to be such that it wants to oppose the cause producing it. So since the north pole is going away, south pole is generated and it's saying please don't go away from me, because it wants to oppose the cause producing it. Okay, the same story is true if the south pole of the magnet is brought closer. And likewise, the south pole of the magnet is taken away. The same story. Only thing is here, when you're bringing the south pole closer, south pole is generated and north pole at the other end. Likewise, when you're taking the south pole away, north pole is generated here and south pole over here. So this is what is called electromagnetic induction. Okay, we've already seen that whenever current flows through a circuit or through a wire, through a conductor, so to say, it generates a magnetic field of its own. So current can generate magnetic field. Likewise, here what we are saying is the change in magnetic flux. So to say, a magnetic field is generating current. It is these two phenomena, current generating magnetic field and magnetic field in turn generating current, which proved that electricity and magnetism are one and the same thing. Before these phenomena were discovered, okay, electricity and magnetism were completely two different fields. Okay, it is because of this phenomenon, current generating magnetic field, and then magnetic field generating current, which proved that electricity and magnetism are one and the same. Thereby, these days we have the name electromagnetism. If you wish to draw, you can pause the video and draw this. Alright. Let us therefore very quickly give a look at Faraday's laws of electromagnetic induction. My chalk is very bad. Okay, so Faraday's laws. You know there are two laws you studied in class 10 also. The first law says, what does it say? Whenever the magnetic flux, I hope you have your exercise books and a pen ready. Okay, so as I am saying, you can also write whenever the magnetic flux linked with a circuit, or rather you can also say a coil, whenever the magnetic flux linked with a coil changes and EMF is induced, and EMF or current is induced in the circuit, which is given by, or which is equal to the rate of change of magnetic flux. Okay, this is the first law of Faraday, or Faraday's first law. So see. Okay, so this law is telling us that the EMF, if E is the EMF induced, then EMF induced is equal to delta phi B divided by delta T. Now what is this phi B, or rather delta phi B? Delta represents a change and phi B magnetic flux. So therefore delta phi B is the change in the magnetic flux, and this change in magnetic flux takes place or happens in time delta T. Alright, so this is it, and let us also write the second law. The second law, mind you, is also something called Lenz's law. Second law. It says the induced EMF, or the effect. This is the effect, mind you, is in such a direction that it wants to oppose the cause, reducing it, and this is also called, by the way, Lenz's law. Lenz's law. Apostrophe S, Lenz's law. Alright, class 12. Okay, so this is also, by the way, called Faraday's second law. When we incorporate both of these two laws, so we get E is minus of delta phi B by delta T. This is a small t by delta T. The minus sign tells us that the EMF induced is in such a direction that it wants to oppose the cause. So the minus sign comes from the Lenz's law, remember. So this is about Faraday's laws. So I'm going to erase this. So the EMF induced has magnitude this much. Oh, by the way, if delta t is very small, the change in time is very small, then the change in magnetic flux will also be very small. So therefore, this very thing can also be written as minus d phi b by dt. Completely skipped my mind. Okay. Now, if there are n number of turns in the circuit, if there are n turns in the coil or in the circuit, then E will be equal to minus d of n phi b, because the magnetic flux linked with the coil which has n turns will be n phi b. So d n phi b is the change in magnetic flux linked with the whole coil, dt. Now since the number of turns is a constant, n can be taken out of the differentiation, so to say. So this becomes minus n d phi b by dt. Alright, so this is another equation. Can I erase this? Okay, I hope you would copied. So thereby we can finally write E is minus n d phi b by dt. This is, so to say, the final expression for Faraday's laws.
Now if R be the resistance of the circuit, then the induced current I is equal to E upon R according to Ohm's law, so which is equal to minus n upon R d phi b by dt. Now whenever the magnetic flux linked with a coil or a conductor is changed, we have seen that an EMF is induced in it. Now the direction of the EMF induced or the direction of the current induced whenever the magnetic flux linked with a conductor is changed is given by your Fleming's right hand rule. I haven't written the statement for Fleming's right hand rule here because I want you all to write the statement yourself. You've done Fleming's left hand rule, it's exactly the same. Only thing is, this is with regard to your right hand, don't forget. So you again here also do remember your F, B, I, like in case of your Fleming's left hand rule. Now F gives the direction of the force. Your forefinger gives the direction of the magnetic field and your middle finger gives the direction of the current induced. So Fleming's right hand rule tells us if we stretch the thumb, the forefinger and the middle finger, of course that of our right hand, don't forget to mention which hand you are talking about. Alright, so if we stretch these three fingers at mutually perpendicular direction like you can see, then if the thumb gives the direction of the force applied, the forefinger gives the direction of the magnetic field, then the middle finger gives the direction of the current. So in this case, we have a conductor over here and you can see the direction of the force here is towards the right hand side. The magnetic field is penetrating into the plane of the board. So thumb gives the direction of the, force. Your forefinger gives the direction of the magnetic field, thereby the current is induced in the upward direction. So this is what Fleming's right hand rule tells us, remember. And it gives us the direction of the induced current. So here, in case of this conductor, current is induced in the upward direction, mind you. So current goes in the upward direction. So let me just give it this way. So current is induced in the upward direction.